Okay, so we've done two problems using Excel. One was the homework assignment problem that we did by hand first, demonstrated how to do it in Excel. The second was this allocation model. An allocation model is just a linear optimization problem where you're maximizing an objective subject to less than or equal to constraints. Okay. Another kind of optimization problem, linear optimization problem, we would call a covering model, which is the opposite. You're minimizing an objective subject to greater than or equal to constraints, such as you're trying to minimize cost while not going less than certain demand. That is, you have to do at least a minimum amount, but you want to find where along those minimums is the lowest cost. Okay, so that would be called a covering model. We'll see an example of that here. So, Dalby Outfitters wishes to introduce packaged trail mix as a new product. So we're going to make trail mix for people to eat. The ingredients there's 5 different ingredients: seeds, raisins, flakes, pecans, walnuts. Okay, so 5 different things to put in the trail mix. Each ingredient contains a certain amount of 4 nutritional related things: vitamins, minerals, protein, and calories. The marketing department has determined that the product be designed to meet certain nutritional requirements. That is, a minimum amount of vitamins, a minimum amount of minerals, and so forth. Okay, so these are going to be our greater than or equal to constraints. Right? We want to find where along those minimum requirements we can achieve the lowest cost. So we're minimizing cost as our objective function. So here's the parameters. So we have our 5 ingredients: seeds, raisins, flakes, pecans, and walnuts. We know how many grams of the different nutritional things, vitamins, minerals, proteins, and calories, exist per pound of those ingredients. So for a pound of seeds, sunflower seeds, I guess, you'd get 10 grams of vitamins. You'd get 5 grams of minerals. You'd get 1 gram of protein. For 1 pound of raisins, you get 20 grams of vitamins, right? More minerals, more protein, and so forth. And then, of course, we have our requirements. These are our constraints that say you have to have at least 20 grams of vitamins. That is, you need to find the mix of how many pounds, right, of each of these ingredients, such that you at least have 20 grams of vitamins, at least 10 grams of minerals, at least 15 grams of protein, and at least 600 calories, grams of calories. And then obviously for our objective function, we have to pay for those ingredients, right? Per pound, this is how much they cost. Okay. So let's take this information. We're going to copy this into Excel. We're going to create a model, okay, to solve this. I'm going to put it down here so it's a little bit out of the way. So let's again start with our decision variables. So we have seeds, raisins, flakes, pecans, and walnuts. Okay. I don't know. Let's do 1/10 of a pound for each one, just to start with. Okay. We're going to make those our decision variables. As I always do, I like to highlight that. So there we go. So that's part 1 of the model. We know what we're deciding, that the pound amount of each ingredient to buy to make our trail mix. Step 2, objective function. Okay. The objective function is going to be a linear function of our decision variables. So we're just going to take those cost values and we're just going to compute the sum product, our decision variables multiplied by their corresponding cost, all added up, and that will become our objective. Okay, we'll make that dollar amount. Let's make it 2 decimal places. So in this case, if we got 1/10 of a pound of every ingredient, the trail mix would cost $2.50 per pound. Sorry, per bag of the trail mix. Okay. And then finally, let's do our constraints. Now, the reason we call this a covering model is we're trying to choose, in this case, ingredients such that we cover minimum requirements. In this case, minimum nutritional requirements. Okay, so I'm just going to copy all those parameters up. Okay. In this case, these are the constraint values. They're all less than or equal to. Okay. That is, we want to compute how many grams of vitamins do we get from this particular mix of ingredients, and we're going to constrain that to say, not less than or equal to, greater than or equal to. Somebody should have challenged me. Minimum requirements. So we can't go below 20 grams of vitamins, 10 grams of minerals, and so forth. So again, some product will be our friend for the next couple weeks. So that multiplied by these parameters, I'm going to use absolute addresses for the decision variables because they're always in the same place. We're going to copy this formula down, different parameters, but the same decision variables, each one. Okay. So we'd see here, this particular solution, 1/10 of a pound each, does not meet our constraint for vitamins. It does not meet our constraint for minerals, protein, or calories. It's not enough of ingredients, right? So, and just so we can visually identify it, let's use our typical if the value equals, and actually, I don't want to confuse anybody, but just for now I'm going to say if it's less than or equal to the constraint, we're going to say that's a binding variable, otherwise it's not binding. Now the only reason I'm going to use less than or equal to is so you can see here this invalid solution is violating constraints, right? So I'm listing them now as binding. That is, these things are trying to bind this solution, but I've violated it, okay? Now, the last thing, of course, would be to say you can't have negative ingredients. Again, that's going to be important, one, because it might be nice to take negative ingredients because that would certainly lower cost, but you could also think about negative ingredients offsetting other things and so forth. So I'm going to make sure we have selected to assume non-negative decision variables, okay, as opposed to create 5 different constraints to say that each thing has to be greater than or equal to 0.
Is there an option in there also to make them whole numbers, like we have to buy at least 1 pound of each?
Yeah, so the question was, is there an option to make them whole numbers so that we could say something like you have to have, the multiple of 1 of each? The answer is yes, and the real answer is that's actually called integer optimization, which is a special class of linear optimization, where everything has to be integers. Yeah. So we'll actually get to that next week. All right, so with all of that, let's tell Analytic Solver Platform, here are our decisions. Tell it this is our objective we want to minimize. And tell it these 4 values here are the constraints we want to set as minimums bound by these variables. Okay, and solve. So, green message. Solver found a solution, all constraints are satisfied, and optimality is achieved, right? So, again, we'll ask some of the standard questions. First, what's the pattern of the optimal solution? The pattern is we should only use seeds and raisins and flakes because they're cheap, presumably. Pecans and walnuts are a more expensive ingredient. They may give us more nutritional value, but if you think about it, let's take, for example, the walnuts. You can get 20 grams of vitamins for $6 if you chose walnuts. You can get the same 20 grams of vitamins for only $5 by using raisins, right? Intuitively, that's why the solution for optimizing a minimal cost said don't bother with pecans and walnuts, right? Because they're too expensive. You can get the same nutritional requirements to be met by using cheap ingredients, just using a little more of them, maybe. Okay. So the pattern to the solution I would describe as use seeds, raisins, and flakes. Right. In this case, we're using flakes mainly. Okay. So 1.3 pounds of flakes for less than half a pound of seeds and about 1/3 a pound of raisins. Why? Probably because flakes are cheap. Right. They're the cheapest ingredient. We can get a lot of nutritional value out of just flakes. Now, the next question would be, what's the optimal solution function, objective function? And that would be $7.54, right? So the cheapest trail mix we can make, given these ingredients and their costs for these nutritional requirements, is a $7.54 bag of trail mix. Okay. Last question, what are our binding constraints? In this case, we have 5 decision variables, so there should be technically 5 or more binding constraints. Okay, so when we had a 2-variable system, we said there will always be 2 binding constraints, maybe more. Right? For a 5-variable decision or 5-variable problem, there should be 5 or more binding constraints. First, pecans and walnuts are bound by being positive. Okay, we might have chosen negative pecans, negative walnuts, but we weren't allowed to. So those are at their minimum. Beyond that, there are 3 other binding constraints, the ones for mineral, protein, and calorie nutrition requirements. So those in some way form a constraint space for seeds, raisins, and flakes that prevented us from choosing lower values of any of those, right? If we had chosen fewer seeds, so let's just try. So for 0.47, let's say if we had only chosen 0.4 pounds, we would have violated actually all 3 of those nutritional constraints. Right? So we probably would have needed to up raisins. Well, if we do that, right, we're going to increase costs. So we lower cost by choosing less seeds, but increase cost by choosing more raisins. Right? To meet all these constraints, the optimal solution said something like 0.47 pounds of seeds. Okay, so that's the optimal. All right, any questions about making the model, identifying constraints or binding constraints, or describing the pattern of the optimal solution? Okay. You will be asked on the assignment to describe the optimal solution. Okay, that can be answered in many different ways. Okay, so I'm not looking necessarily for one specific answer. If I were answering that question for this particular problem, I would say something to the effect of, we use no pecans and walnuts and mostly flakes. That is, more flakes than anything else, no pecans and walnuts. That's the pattern of the optimal solution. That's sort of a text or a word description of what the optimal solution looked like. Okay, the optimal decision variable values. Okay, the optimal cost, objective function, $7.54. All right, let's extend this problem. It might be the case that even though we chose 0 pecans, 0 pounds of walnuts, we might want to say we at least want to choose a little bit of everything. That is, nobody wants a bag of trail mix if it only includes a couple things, right? They want variety. That's why you get a mix of things. So let's create 5 new constraints to say we want a minimum amount of each ingredient. Okay? So I'm just going to call these the min ingredient constraints. Okay? And I'm just going to use 1 times each ingredient, okay, in 5 different lines. And I'm going to constrain each of those, like before, to be greater than or equal to some minimums. And let's just say we want to say, let's at least include a 1/10 of a pound of each ingredient. Okay, that is, nobody wants a trail mix if it doesn't include a little bit of everything, and we don't want to include, a minuscule amount of anything. We want at least a 1/10 of a pound of each thing. Okay, so those are 5 new constraints. I need to tell Analytics Solver Platform about them using the standard approach. Okay, and now with those 5 new constraints, obviously we're violating 2 of them right now. We need to re-optimize, find a new optimal strategy. So now, right, we have a new solution, right? Costs more than before because we've further constrained the space, right? We've made the old optimal solution invalid by creating more constraints. So we have a new solution. By definition, it has to have 5 or more binding constraints because we have 5 decision variables. What are the binding constraints? Well, it's still minerals, proteins, and calories, but now it's not a minimum of 0, it's the minimum of 0.1 for pecans and walnuts. So effectively, the pattern still held of choosing the minimum amount we could of pecans and walnuts, because they're expensive, and then filling the rest of the bag with mostly flakes, some seeds, and even fewer raisins to meet the nutritional requirements. Okay. And obviously we could choose less of those other 3 ingredients now that we have to choose more of pecans and walnuts. But we still chose as few of them as we could to meet the nutritional requirements. So still 5 binding variables, or 5 binding constraints for the 5 decision variables. All right, let's do optimization sensitivity. So one might ask, let's just pick a constraint. Let's say that the constraint was, let's do calories. Let's say, what minimum amount of calories could we stand before the optimal solution pattern starts changing in different ways? So let's do a parameter for the 600 here. So 600 calories, we're going to make that a optimization parameter and say, let's change that, find a new optimum, and describe it. Okay. So we'll make the upper value 600, like it used to be. And I don't know, let's go all the way to 0. Why not? Okay. So between 0 and 600, okay, we're going to create now a new optimization sensitivity report, parameter analysis. You can't see it on the screen up there. So now you'll see we're on sheet 3. Okay. So I-12 is where the parameter is. We have, what was it, between 0 and 600. Well, we'll just do 21 access points. That's good enough. Our objective is G6. Our variables, 5 variables there. Let's create the report. So this is just automatically changing that parameter to 21 different values and optimizing each time, and then collecting up the results. Okay, so what do we see? Well, because we started at 600, we're going to start at the bottom here. So with 600 calories, we knew the optimal parameter, or the optimal solution, was an $8.04 bag of trail mix that had the minimum amount of pecans and walnuts, mostly flakes, some seeds, even fewer raisins. If we went down to 570 calories, we could make a cheaper trail mix bag, right? Because that constraint was binding. So if we lowered its limit, we could find a better solution, right? In this case, one that only cost $7.95, still using minimum amount of pecans and walnuts, but using slightly less flakes, a lot less seeds, but more raisins. So the pattern to the optimal solution changed, right, once that binding constraint was changed. So if we would allow for less calories, it becomes optimal to use raisins over seeds, as opposed to seeds more than raisins, right? Somewhere between 540 and 570 calories, the calorie constraint stops becoming binding, right? And beyond that, our solution never changes, right? So somewhere in that range is sort of a break-even point, what we would call, in economics, they call it a shadow price. You're usually talking about price of things. It's the price at which, or the point at which, something breaks even and no longer matters, or no longer is profitable, or no longer is important. So somewhere between 540, 570 calories no longer become important as a binding constraint. What does become a binding constraint? You can look at this and tell. Not always, but in this case you can. So what became the new binding constraint when calories no longer was binding the solution? The minimum ingredients for whatever this ingredient was, which happens to be seeds, right? So remember, if we allowed less calories, we would use fewer seeds, more raisins. We kept making that decision up to the point where we used the minimum amount of seeds, right? We could use no fewer than 0.1 pounds of seeds. So once we hit that constraint, it didn't matter how much fewer calories we would allow. We were stuck with the minimum amount of seeds and however many raisins and flakes we needed to make up for the other two binding constraints, minerals and protein, I think it was. Yeah. So, optimization sensitivity, answering our question of a few different questions. One is, how does the optimal solution change with changes to the minimum caloric count? And at what point does the caloric count, the calorie grams, no longer become a binding constraint, no longer limit the solutions? At that point, something else becomes binding, something else limits the solution. Okay? And in this case, we know it was the seeds, minimum seeds. All right. We're going to whirlwind tour, talk about one more kind of model. Okay? So we talked about allocation models, maximizing an objective subject to minimum constraints. Subject to maximum constraints. We talked about a covering model, minimizing something subject to minimum constraints. Okay. A new kind of model, or a different sort of type of linear optimization model, is called a blending model, in which you have a constraint which is on the some proportion or percentage of a decision variable. Okay, so what you'll see is something like this. Let's say, for example, you had 3 decision variables, x, y, and z, and you had a constraint that said the proportion of x to the sum of all the decision variables must be greater than or equal to 25%. That is, I want the value of x to be at least 25% of the total of x, y, and z. Okay, I want a minimum percentage or a minimum proportion. So we're in some ways blending multiple decision variables in the same constraint. Okay, you could write that like this: x divided by x plus y plus z is greater than or equal to 25. Okay, that's intuitively how you would say the fraction or proportion or percentage of x to the total amount of x, y, and z is restricted to be at least 25%. However, this constraint is not a linear function, right? It involves division of one decision variable by some others, right? That would be a nonlinear model. That is, it can't be a linear model because it involves a nonlinear equation. However, these kinds of proportions, where you just say the proportion of one decision variable to the others, can be rewritten as a linear equation. Okay? Just using some algebraic manipulation. Let's say we took that equation, multiplied each side by x plus y plus z. Right? So what you would get is x is greater than 0.25 times the quantity x plus y plus z. Right? So just algebraically, we move the denominator to the numerator of the other side. Okay? You could further, so you expand this right-hand side out. You could say x is greater than a quarter x plus a quarter y plus a quarter z. Okay? Same equation, just manipulated to look a little different. And then you could manipulate that, because we like all the decision variables to be on one side of the inequality. We can manipulate that to say 3/4 x minus a quarter y minus a quarter z has to be greater than or equal to 0. Just algebraically manipulating the equation. Blending models involve a constraint on a percentage of decision variable values, which you could write intuitively in something like this form. However, you can always convert them to something like this form to make them a linear function in order to use a linear optimization approach, okay, to solve the problem. Now, I haven't told you why you should prefer linear optimization approaches to a approach of nonlinear optimization. We'll get to that later. But this is just to help you understand a new kind of constraint type and how we could make it fit our pattern that we've been using. You could use some product, right, to compute this part of the equation, and then constrain the value it produces to be greater than or equal to 0, and that would look like every other kind of constraint we have, okay, for a linear model. So let's take an example here. We're going to make coffee. We have 3 kinds of coffee beans: Brazilian, Colombian, and Peruvian. We're going to mix them together to make our coffee bean mix, or our coffee ground mix, okay? The thing is, these 3 different kinds of beans have different aromas and different strengths as far as the taste. Somebody has come up with values for that, okay, per each bean type. And we want to make a ground coffee mix that has a minimum aroma rating and a minimum strength rating. Okay, so one of these kinds of beans smells better than the other. One of them is stronger coffee than the other. We want to mix them all together to make a minimum aroma amount and a minimum strength amount. Okay, subject to probably lowering cost because we have to pay for these ingredients. Okay, now we also want to make a minimum amount of the coffee for 4 million pounds. So the question is, how many pounds of each of these 3 types of beans do we need to buy to make a total of 400 million pounds of coffee for the lowest cost possible? Okay, and here's a table summarizing the parameters of that model. Okay, so we have our beans, we have the aroma rating for each one, the strength rating for each one, the cost for each one, and the capacity, well, the amount that we can buy. So we can buy no more than 1.5 million pounds of Brazilian beans. That's just how many we have available to buy. And we want to buy a total of 4 million pounds worth. And we want to mix them in a way to meet a minimum aroma and strength rating in order to minimize cost. Okay? All right. So let's do this in Excel very briefly. Okay, decision variables. We have our Brazilian beans, we have our Colombian beans, we have our Peruvian beans. Okay, so I don't know. Let's assume we want 1 million pounds of these, 1 million pounds of these, and 2 million pounds of these. Okay, just as a starting point to sort of illustrate what we're computing. We have our objective function, okay, which are these costs, okay, multiplied by the amount of each bean, okay, so sum product. So that's the cost of that amount of beans that we're going to purchase. That's our objective function we want to minimize. I'm going to highlight it green. And then we have our constraints. And the constraints are where things are going to get a little tricky, okay? Because we have a constraint on aroma, okay? Now, we know the aroma rating of each bean, right? So we could compute the sum product, right? So number of beans multiplied by the aroma rating. The problem is, right, we want each pound of coffee to have a minimum aroma rating, right? Now, one way you could do that, this is a blending constraint, because now we need to divide this value by the total of all these values, right? Which means we have a constraint function with the decision variables in a numerator and the denominator, right? Not a linear model anymore, right? Okay. Now, one way you could do that would be to say, if we want a minimum rating, we want a minimum rating of, I think it was 78, multiplied by the sums of these things. Okay? What that essentially does is it makes the left-hand side of this inequality a linear function and the right-hand side a linear function. Right? I'm going to go back to the slide real quick. Effectively, what we did is we chose to write something like this as our constraint. So an inequality that has decision variables on both sides, okay, but it's a linear function on both sides. That's okay. Right? We could also have written this as, well, if we're just taking 78 minus the total of these things, right? So 75, well, I'm not going to do all the math in my head, but you could take 75 times your Brazilian beans minus, right, 78 times your Brazilian beans, right? That'd be -3. This one would be, right, whatever 60 minus 78 is. This would be 85 minus 78. Right? You could do all that, right? And that way you could move the right-hand side values to kind of the left-hand side and say this must be greater than or equal to 0. The sort of last form we saw the constraint in the slide. Okay, that's two different ways you can do it. At this point, things are linear. I'm happy, right? So let's talk about strengths. Same thing. So our sum product. These multiplied by these. Let's make sure those are a minimum amount. I don't remember what the let's see, minimum strength of 16. Okay. So this side is 16 times the sum. You could add them all together if you wanted to. I'm just going to use the sum function, sum of those. Okay. And now these constraints become very simply just the constraints of each bean type. So you can't choose more than 1.5 million Brazilian beans. You can't choose more than 1.2 million of Colombian beans and so forth. So now we can mark our decision variables, mark our objective. This is cost we want to minimize. All of these constraints are constraints we want to make minimums, so we want to constrain them to be greater than or equal to these minimum values. And then finally, we want to assume you can't have negative amounts of any beans. Right?
Did you say that we can't have more than that many pounds?
Oh, yes, you're right. Thank you. Got ahead of myself. First two constraints are minimums. And the last three were maximums. Thank you. That's why I didn't fill that in yet. Oh. Okay. So these three values computed have to be less than or equal to. So at this point, you know we're not doing a allocation or a coverage model. We kind of have constraints of both kinds, minimums of things and maximums of other things. So we have sort of minimum requirements of aroma and strength. We have maximum availability of ingredients. And again, assumed implied constraints of you can't have 0 of anything. Okay? Or I'm sorry, you can't have less than 0 of anything. So let's solve. Okay. Oh. No. I think we were right. You couldn't have... Oh, there was one more constraint. What was the last constraint? So obviously the optimal solution in this case is don't buy any beans. It's the cheapest thing you can do. What was our other constraint that I forgot? Yeah, I'm going to call it the demand, which is if you just take all the beans and add them up, we need to make at least 4 million pounds, right? So there was one more constraint. So obviously, we were violating that constraint here. Let's find out. So if this value equals this one, this is a binding constraint, otherwise it's not binding. And let's make all that. resolve. There we go. That looks a little better. So the pattern of the solution, right? Buy as many Brazilian beans as you can, 1.5 million, and then a mix of Colombian and Peruvian beans, right? Such that you meet the minimum aroma rating. Okay, that's the binding one. And obviously such that you get enough pounds of beans, right? So the 3 decision variables, 3 binding constraints. One is our minimum demand. We had to buy 4 million pounds of beans, right? In some mix. So obviously, to minimize costs, we'd want to buy just 4 million pounds. We don't want to buy more than we need if we're trying to minimize our cost. Next minimum constraint, we bought all the Brazilian beans we're allowed to buy, presumably because they have a relatively high aroma rating and they have the minimum strength, but they're also the cheapest, right? So we want to buy more Brazilian beans than anything else, or as many Brazilian beans as we can, because they give us a decent aroma and they're really cheap. Okay? And then the last binding constraint was the aroma constraint, which basically said, well, if you're going to use that many Brazilian beans, you need a certain amount of Peruvian beans to offset the Brazilian and Colombian beans to give you the minimum aroma rating of 78, right? A mixture of 78. So those are the 3 binding constraints. That's the pattern, and the optimal objective is $2.4 million, roughly. Any questions? So at this point, we've seen 4 linear optimization problems, 4 models, every one we made using this same pattern. Identify your decision variables, identify your objective function, identify your constraints. Compute, make them in Excel model, right? I always put them in this order. You wouldn't necessarily have to. It just naturally makes sense, right? If you use the pattern I've used here, where you have your decision variables in a row together, both your objective function and every constraint function becomes some product of some coefficients multiplied by your decision variables. In the case of a blended constraint, you either need to do a little math manipulation or at least some thought process into how you turn the constraint function into a linear function of the decision variables. That can be a linear function on the left-hand side and the right-hand side, if you want it to be still linear. Or you could do the further manipulation to sort of make it all on the left-hand side, and the blended constraint would always be greater than or equal to, or less than or equal to 0 in that case. So the right-hand side would be 0 if you move this linear function over to the left-hand side of this constraint equation. Oops. All right. Assignment 4 should be posted on Blackboard. It's due next week, like all assignments are. It involves 2 linear optimization problems. One of them has blended constraints. Okay. Each one will ask you to build a model in Excel like this, and I believe it will ask you to describe the pattern of the optimal solution. So once you've solved, what does the optimal decision variables look like? Did you do, a minimum amount of something? Did you do the maximum amount of something? Just describe to me what the pattern looked like for the best solution. What's the best objective function value? Which constraints are binding? And then both problems will ask you to do some kind of optimization sensitivity. So given some parameter to some constraint, or you could do, so we didn't do an example of this. Let's say we did a optimization sensitivity in the cost of Brazilian beans. That is, how expensive would Brazilian beans have to be per pound before we stop buying them, as many of them as we could, right? Intuitively, you might think, well, once they're 60 cents, like the Colombian beans, maybe we'll start buying more Colombian, right? I don't know. You could use optimization sensitivity to ask that question by creating an optimization parameter and running the optimization parameter analysis report, okay? You'll need to do that on the assignment. one way or another. It'll ask you about one parameter of the whole model, how much it would need to change by, or how, when it changed, does the optimal solution change? Does the optimal decision variables change? Okay. All right. In that case, next week, okay, what we didn't quite get to, but that's okay, is more kinds of linear optimization models. Okay. So next time, we'll just discuss more types, special types of linear optimization. One we've seen a preview of is integer optimization, where things are whole numbers. There's other kinds as well. And then if we have time, we'll talk about nonlinear optimization.